Respected viewers, today we are going to have a look at flash type ADC. Now let's move on. What are the different types of analog to digital converters available? Before we could have a talk about flash type ADC, let us try to understand and have a knowledge about what are the different type of analog to converters, analog to digital converters which are available. Now the first type is flash type AD converters. Then we have counter type AD converters. Then we have servo tracking AD converters. And a very popular one is successive approximation register, that is SAR type AD converters. What we'll discuss today is the internal structure, the functionality of flash type ADC. Now let's have a look at the internal diagram of the flash type ADC. Now before we proceed forward to understand the function, how it functions, let us try to have a very brief look into what is there inside the flash type ADC. Now we are going to discuss a simple 3-bit ADC, and a 3-bit ADC here consists of a priority encoder. It is having 8 inputs. Obviously it will have 3 outputs, that is 2 to the power 3 is equal to 8, so it will be able to handle 8 inputs. Now here the inputs are priority based. That means the least priority is of x0 input, x1 is having priority greater than x0, x2 is having priority greater than x1, x3 is having priority greater than x2, and so on. So even if we have a trigger input at x0, and if there is a trigger input at x1, then the trigger input at x0 will be ignored. Rather, the information will be processed only for x1 at the output. So keeping this in mind, let's move on to the next part. Here we can see the inputs are connected to comparators, which are constructed out of operational amplifiers. Again, they are connected in open loop configuration. So there are eight comparators, right from one that is the connected to x0 to the to the eighth one, which is connected to x7. Now the non-inverting terminal of all the operational amplifiers are tied up together, and here where we provide the unknown analog input, we will denote that as VA. The other pins that are the inverting pins are connected via a potential divider resistive network. Each resistor, that is, we have 1 2 3 4 5 6 7 8, we have 8 resistors. All the values of the resistors are the same, so we have denoted that as R here. What is the purpose of this resistive network is a potential divider, and it will divide the entire potential, that is the reference voltage VR, it into this many voltages, where the bottom one is connected to 0 and the first one, that is V1, is 1/8 of VR, V2 is 1/4 of VR, V3 is 3 by 8 VR, and so on. So this type of a flash type ADC is having 3-bit resolution, since it is having 3 bits at the output, and a step size of 1 volt. Now let's try to understand the other sections of this. We have already discussed that it is comprised of 8 operational amplifiers. 8 operational amplifiers output are connected to the input of the priority encoder, and we have the resistors which make the potential divider. Now let's see how do we get 1 by 8, 1 by 4, 3 by 8, this sort of a voltage division at the nodes of this. Now just try to have a look at V1. So V1 voltage is across this R. So to get the voltage V1 with respect to VR, what we have to do is we have to take this divided by the entire resistance multiplied by the voltage which is applied across it. So if we look into this, here we can see V0 is directly connected to ground, hence it is 0. Then we have V1, the resistance with respect to ground is this resistance by the total resistance multiplied by the reference voltage. So what we can see is we have R, then there are 8 R's, this is the total resistance 8R. So R gets cancelled, what we get is 1 by 8 VR. So in this manner, if we calculate the other values, we will get 1 by 4 VR, 3 by 8 VR, 1 by 2 VR, 5 by 8 VR, 3 by 4 VR, and 7 by 8 VR. Now let's have a look what happens to the voltages. What happens to the comparator when a different type of voltage appears at the input of the comparator. Now suppose we have VA at the non-inverting terminal, and reference voltage VD, or the or the voltage that is because of the because of the potential dividers. So what we can see is VA, if VA is greater than VD, then the output will be 1. So again I'm repeating, if VA, that is the voltage which is applied at the non-inverting terminal, is greater than the voltages at the inverting terminal, then as per the open loop configuration of the op amp, the output will be at positive high. So I will expect a 1 at the output of the comparator. Then if VA is less than VD, then the output will be 0, and if both the potentials are same, it will hold the previous value. Now let us try to understand a situation. Now suppose the input voltage VA is greater than 0. VA, which is applied here, which is again connected to all the operational amplifiers, but the potential is greater than 0 but less than 1 by 8 VR, then the output of the comparator X0 will be high. Since VA is connected to the positive terminal of, that is the non-inverting terminal of the first comparator, and the other is 0, so if the potential VA is greater than 0 but it is less than 1 by 8 VR, then this output will be high and others will be low. So if X0 input is high, which means the priority encoder's output will be all 0. Now let's have a look at the second possibility, that is when the input VA is between V1 and V2. That is between V1 and V2. That means it is the output X1 is high also x0. So this one is also high and this one is also high, but since the priority of x1 is greater than x0, we will get 0, 0, 1 at the output. So similarly, if we try to analyze each and every input of this comparators, we are summing it up in a table where we have all the inputs of the priority encoder, and we have the input voltage range. Now if it is between 0 to 1 by 8 VR, then we can see x1 is 1 and the output are all 0. Similarly, if it is between 1 by 8 VR to 1 by 4 VR, then x0 and x1 as well are high. Since the priority of x1 is greater than x0, output will be 0, 0, 1. Similarly, in the next case, x1, x0, x2 are all high, but x2's priority is greater than x1 and x0, and hence we get 0, 1, 0. So similarly, if the input voltage is between 7 by 8 VR to VR, then x7 is high, and obviously we get the last combination. So this is how an unknown input voltage is compared inside the analog to digital converter, and the corresponding digital output is available at the output of the analog to digital converter. So this is how a flash type AD converter functions. Thank you very much for watching this video, and in the next video we will have a look at the successive approximation register AD type converters. Thank you very much.